There's something profoundly human about looking at the night sky and feeling the call of the stars. Since our ancestors lit the first fire and gazed at those luminous points piercing the darkness, one question has echoed through the millennia: what's out there? For decades, science fiction has sold us a glorious future. Enterprise ships crossing galaxies at warp speed, human colonies scattered across distant star systems, Matthew McConaughey navigating through black holes while his daughter ages on Earth, Elon Musk promising cities on Mars before 2050. The narrative is always the same. Cosmic expansion is inevitable. It's just a matter of time, money, and political will. And why not believe it? After all, in just 66 years, less than a human lifetime, we went from the Wright brothers' first powered flight to man landing on the moon. If we achieved that, why couldn't we take the next leap? Why not Alpha Centauri? Why not Andromeda? Technology is advancing exponentially. Quantum computers, artificial intelligence, gene editing, nuclear fusion. Each passing year, yesterday's impossible becomes today's routine. It seems reasonable to imagine that in a few decades or centuries, we'll develop warp drives, perfect cryogenic hibernation, or find shortcuts through the fabric of space-time. But what if all of this is just a comfortable illusion? What if reality is far more unforgiving than we want to admit? As you read these words, humanity is trapped, not for lack of ambition or resources, but by the fundamental laws governing the universe. We are confined in a bubble of survival, the solar system, surrounded by a void so vast and hostile, it defies any attempt at comprehension, and the evidence suggests something disturbing. This prison has no exit. Today we're going to deconstruct the interstellar dream, not with nihilistic pessimism, but with brutal honesty. We'll understand why the boundaries of our solar system aren't just arbitrary lines on a space map. They're the walls of a cage from which, most likely, we will never escape. Ask someone on the street where the solar system ends, and the most common answer will be, at Pluto. Some more informed people might mention the Kuiper Belt, that region beyond Neptune filled with icy bodies where Pluto resides. They're all wrong. The true limit of the solar system is the Oort Cloud, a structure so colossal, it makes Pluto look like a grain of sand on Copacabana Beach. Imagine a giant spherical shell composed of billions, perhaps trillions, of frozen cometary nuclei, enveloping the entire planetary system we know. The Oort Cloud extends from approximately 2,000 astronomical units, AU, to 100,000 AU from the Sun. For context, 1 AU is the distance between Earth and the Sun, about 150 million kilometers. Pluto orbits at just 40 AU. Do the math. The Oort Cloud begins at a distance 50 times greater than Pluto's and extends to a distance 2,500 times greater. It's a frontier that transforms all our space achievements into timid steps inside the house. And here's the fact that should freeze the blood of any space enthusiast. Voyager 1, launched in 1977, is traveling at approximately 61,000 kilometers h, the fastest human-made object in motion relative to the Sun. After nearly 50 years of uninterrupted journey, it has barely left the heliosphere, the Sun's magnetic bubble, and is about 160 AU away. At this absurd speed, Voyager 1 will take about 300 years just to reach the inner edge of the Oort Cloud, and another 30,000 years to cross it completely and finally exit the solar system. Read that number again, 30,000 years. To put it in perspective, 30,000 years ago, humans were still hunter-gatherers painting animals on cave walls. There was no writing, civilization, agriculture. And to leave our own planetary system, we would need a journey spanning that entire historical period, and that's traveling in the fastest ship we've ever built. Leaving the solar system isn't like crossing an ocean. It's not like going from Sao Paulo to Tokyo, or even from Earth to the moon. It's like trying to cross an entire continent on foot, naked, without food, without water, and without oxygen, knowing you'll die of old age before completing the first 1% of the journey. And that's just to leave home. We haven't even started the trip to the nearest star. Proxima Centauri is the closest star to the Sun, our cosmic neighbor. The distance? Approximately 4.24 light-years, or about 40 trillion kilometers. Numbers like these are cognitively impossible to process, So let's use an analogy. If the sun were a basketball in Sao Paulo, Earth would be a pinhead 26 meters away. Neptune would be 800 meters away. Voyager 1, after 47 years of traveling, would be about 4 kilometers away. And Proxima Centauri, it would be in Brasilia 1,148 kilometers away. With current technology, reaching Proxima Centauri would take about 75,000 years. But that's with current technology, you might argue. What if we develop something better? Great. Let's be optimistic. Say that in the not-too-distant future, we develop a revolutionary propulsion system, perhaps nuclear fusion, or laser solar sails capable of accelerating a ship to 10% of the speed of light. That's extraordinarily faster than anything we have today, a feat that would require technological advances comparable to giving Leonardo da Vinci an iPhone. At 10% of the speed of light, the trip to Proxima Centauri would take only 42 years. Sounds manageable, right? A lifetime, but feasible. The problem is that this assumes we can 1. Build a ship capable of accelerating to 30,000 kilometers per zone, 100 times faster than Voyager. 2. Protect that ship and its occupants from collisions with space dust particles, which, at that speed, would have the energy of nuclear bombs. 3. Carry enough fuel or have a functional energy source for 4 decades. 4. Maintain life support systems operational for that entire period. 5. And most importantly, keep human beings alive and sane. Which brings us to the second major obstacle. The human body is a masterpiece of evolution, but only on Earth. We are perfectly adapted for 1G gravity, an oxygen-rich atmosphere, magnetic protection against solar radiation, and a complex microbial biome. Remove any of these conditions, and we begin to fall apart. In deep space, beyond the sun's protective heliosphere, galactic cosmic radiation, GCR, is relentless. We're talking about protons, atomic nuclei, and high-energy particles traveling at speeds close to light, penetrating everything in their path. On Earth, the planet's magnetic field and atmosphere protect us. On the International Space Station, which orbits within Earth's magnetic field, astronauts still receive elevated radiation doses. But in interstellar space, without any natural protection, it would be like being permanently inside a nuclear reactor. The effects are devastating. As with DNA damage, cosmic radiation shatters DNA molecules, causing mutations that lead to aggressive cancers. Studies with astronauts show significant increases in cancer risk after just a few months in space. Neurological damage. High-energy particles pierce through the brain, destroying neurons and causing cognitive decline, memory loss, and behavioral changes. Experiments with mice exposed to similar radiation levels show early-onset dementia. Muscle and bone atrophy. In microgravity, without the constant resistance of Earth's gravity, muscles atrophy and bones lose density at a rate of 1 to 2% per month. After 1 year, an astronaut can lose 20% of bone mass, equivalent to decades of osteoporosis. Immune system compromise. The stress of radiation and microgravity weakens the body's defenses, making trivial infections potentially lethal. The obvious solution would be shielding. But here we encounter another insurmountable problem. To effectively block cosmic radiation, we would need shields of water, polyethylene, or lead several meters thick surrounding the entire ship. This would add tons, possibly thousands of tons of mass to the spacecraft, making it practically impossible to accelerate to relevant interstellar speeds. Some proposals suggest using artificial magnetic fields, but the energy requirements to generate a field strong enough to deflect high-energy particles would be astronomical, literally consuming more energy than the ship could produce. And this assumes we've solved the microgravity problem. Ships with rotational artificial gravity, as in 2001, A Space Odyssey, would require giant, complex structures, adding even more mass and complexity. The conclusion is inevitable. Even if we built a ship capable of reaching 10% of the speed of light, the astronauts would arrive at their destination. If they arrived alive, with destroyed bodies, severe dementia, and terminal cancer, they wouldn't be colonizers. They'd be walking corpses. Every space journey runs into the tyranny of the Tsiolkovsky rocket equation. which relates a rocket's final velocity to the amount of fuel needed. The math is cruel. To move something faster, you need more fuel. But that fuel adds mass, which requires even more fuel. It's an exponential spiral that quickly becomes absurd. Let's do the calculations. Take a crude ship of 1,000 tons, similar to the ISS's weight, to accelerate it to 10% of the speed of light using chemical propulsion. The method we know best, you would need a fuel tank with mass equivalent to millions of times Earth's mass. Obviously impossible. But what about nuclear fusion? Someone asks. Nuclear fusion, the same process that powers the sun, offers an energy density millions of times greater than chemical fuels. It's the great hope for interstellar propulsion. The problem is we still haven't managed to make nuclear fusion work in a controlled and sustainable way on Earth, even with the billions invested in projects like ITER. And even if we succeed, adapting a fusion reactor to work in a spacecraft, with all the demands of miniaturization, efficiency, and reliability, is a technological leap of similar magnitude. But let's be optimistic again. Suppose we succeed. With nuclear fusion, we could theoretically accelerate a ship to significant fractions of the speed of light. But another problem arises: the energy needed to accelerate and decelerate, because you need to stop when you arrive. A 1,000-ton ship to 10% of the speed of light is on the order of 10-20 joules, approximately the energy that all of human civilization produces in 1 year. For a single ship, for a single voyage. And that's not counting the construction cost, life support systems, radiation shielding, communication and navigation systems. The total budget would consume the combined GDP of all nations on Earth for decades, possibly centuries. Faced with biological and energetic impossibilities, some propose an alternative solution: generation ships. The idea is simple but grim. Build a giant, self-sufficient ship and put hundreds or thousands of people on it. They will live, work, procreate, and die inside that ship for generations, perhaps hundreds of them, until their distant descendants finally reach the destination star system. At first glance, it seems like an ingenious solution. But when you stop to think about the ethical implications, the horror reveals itself. You would essentially be condemning thousands of human beings to be born in a metal prison. They will never see the open sky, never feel rain, never walk in a forest or dive in the ocean, never have the freedom to go beyond the claustrophobic corridors of the ship. Their entire existence would be dedicated to a purpose they never chose, keeping the ship running so that future generations, whom they will never know, might perhaps, who knows, reach a distant planet that may not even be habitable. It's generational slavery disguised as a heroic mission. And the practical problems are equally frightening. Inbreeding. With a small, isolated population, genetic diversity would rapidly decrease, leading to accumulating health problems. Social collapse. Studies in isolated environments, submarines, Antarctic stations, prisons, show that confined human groups over long periods develop conflicts, divisions, and sometimes violence. Now imagine this for generations. Loss of purpose. The first generations might have the idealism of the mission. But what about the 5th, the 10th, the 100th? How to maintain motivation when the destination is an abstraction that no one alive will ever reach? Technological failure. A generation ship would need to function perfectly for thousands of years. A single critical system, failing air recycling, water, propulsion, communication, could exterminate the entire population. We are not only limited by physics and biology, we are limited by our own humanity. But what about wormholes, and the Alcubierre drive, and warp drive? These solutions appear constantly in science fiction and even in some speculative academic papers. The idea is seductive. If we can't travel faster than light, perhaps we can bend space-time itself, creating shortcuts through the universe. The problem is that all these proposals run into fundamental obstacles. Wormholes, theoretically possible in Einstein's general relativity equations, but require exotic matter with negative mass to keep them open. There's no evidence that such matter exists, and even if it did, manipulating it to create and stabilize a traversable wormhole would require energies comparable to the mass of entire stars. Alcubierre drive. Proposed in 1994 by physicist Miguel Alcubierre, it suggests warping space-time around a ship, contracting space in front and expanding behind. Again, it requires exotic matter and absurd amounts of energy. Initial estimates suggested mass energy equivalent to Jupiter. Optimized versions reduced this to the mass of a spacecraft, but we're still talking about completely converting mass to energy, something we don't know how to do. Furthermore, there's no empirical evidence that space-time can be manipulated this way. It's interesting mathematics, but it's pure speculation. The harsh truth is that these solutions are the scientific equivalent of magic. They're comforting fantasies that allow us to avoid facing reality. The universe was not designed to be traversed. Interstellar distances aren't bugs in the universe's design. They're features. They're nature's safety mechanism to ensure that species remain isolated, confined to their home planetary systems. And perhaps that's not as bad as it seems. There's a melancholic beauty in our condition. We are alone in our small corner of the cosmos, floating on this pale blue dot, as Carl Sagan poetically described it. There will be no plan B on Alpha Centauri. We won't build a galactic empire. We won't spread across the stars as the movies promised us. But this makes Earth infinitely more precious. Every forest, every ocean, every mountain, every living creature, from whales to bacteria, is all we have, all we will ever have. The solar system is our cradle, our home, and most likely it will be our grave. Instead of dreaming of impossible escapes, perhaps we should dedicate our ingenuity and resources to protecting and healing the only planet we can truly inhabit. Because if we destroy Earth through climate change, nuclear wars, ecological collapse, there will be no rescue ships coming from Martian colonies. There will be no refuge in the stars. The universe gave us a cage, yes, but it also gave us a paradise within it, a living, breathing planet filled with liquid water, breathable atmosphere, and a biosphere of staggering complexity. A cosmic oasis that took billions of years to form. The stars will always be there, shining in the darkness, beautiful and unattainable. We can admire them, study them, dream about them, but we will never reach them. And perhaps, just perhaps, accepting this truth is the first step toward finally caring for the only home that truly matters. The next time you look at the night sky and feel that ancient call of the stars, remember, they are not destinations. They are reminders. Reminders of how vast, indifferent, and fundamentally inaccessible the universe is, and reminders of how precious, fragile, and irreplaceable this small blue sphere we call home is. We are trapped here, and perhaps that's exactly where we should be. May the silence of space teach us to value every voice here on Earth. If this thought touched your heart, subscribe so we can continue exploring these mysteries together. Leave your like so this message reaches more curious minds, and comment below. What is your favorite part of our universe?